Hello everyone. This time we are showing and proving a nice little construction in a square, dividing a line segment in 5 equal parts and using the mid-parallel properties to prove it. We start with a square ABCD. Let's call the middle of the side CD the point E. We will now connect the point A with the point E. Furthermore, let's draw the square's diagonal BD. We need now 2 more points. Let's call F the middle of the side AB, and G will be the middle point of the diagonal BD. Now we will project 4 points on AE. First, we project F on AE. The intersection point is called W. We do the same thing for B. Its projection is called X. The projection of G on AE is called Y. And finally, we project the point D on the segment AE, and the projection point is called Z. Remember, projecting a point on a line means that we draw perpendiculars to that line from those points. The perpendiculars form thus right angles with AE. We can now see that the 4 points W, X, Y, and Z divide the line AE in 5 equal length pieces. I will now pause for a couple of seconds so that you can try to prove this for yourself. Okay, let us prove that the 5 segments are really of the same length. We will do that in several steps. First, we will prove that AW is equal to WX. Then we will prove that XY is equal to YZ. After that, we will prove that AW is equal to ZE. And finally, by showing that AX is the same length as XZ, we show that the 5 are of equal length. In this proof, we will make use of a special line in triangles that is called the mid-parallel. A mid-parallel in a triangle is a line which connects the midpoints of 2 sides of a triangle. That line is parallel to the third side and is, by the way, also equal to half the length of that third side, though we won't be needing that last property. We can do that for each pair of sides, so consequently, every triangle has 3 mid-parallels. In reverse, when a line is parallel to one side of a triangle and intersects the middle of another side of that triangle, that line will cut the third side of the triangle in half. Now then, let's start by proving that AW is equal to WX. Let's consider the triangle ABX. The point F divides AB in half by construction, and WF is parallel to BX because both are perpendiculars on AE. So we can conclude that WF is a mid-parallel in ABX, and thus AW is equal to WX. The second step is proving that XY is equal to YZ. Let's consider for this the concave trapezoid XBDZ. XBDZ is a trapezoid because BX and DZ are parallel sides as they are both perpendicular on AE. In a trapezoid, there exists a mid-parallel, called mid-segment or midline here, connecting the midpoints of the 2 sides, which is parallel to the bases. In reverse, when a line is parallel to the base sides of a trapezoid and intersects one of the other sides in the middle, then it will also divide the fourth side in half. Knowing that, let's look again at the trapezoid XBDZ. We know that G is the midpoint of the diagonal BD, and GY is parallel to the two base sides. So Y divides the XZ side in two, ergo XY is equal to YZ. Now then, we are halfway there. Let's consider the triangles AWF and DZE. These are congruent triangles. Why? Because first of all, we know they are both right-angle triangles. Secondly, the hypotenuse of both are equal in length as they are both half of the side of the square by construction. Thirdly, the angle in A is equal to the angle in E because they are corresponding angles between two parallel lines. Those parallel lines being the square sides, intersected by AE. Now, with right-angle triangles, congruence is guaranteed if the hypotenuse and one of the acute angles are the same. If AWF and DZE are congruent, that means that the side AW is equal to the side ZE. We are almost there now. On the one hand, we have AW equals WX equals ZE. On the other hand, we have XY equals YZ. So we only need to prove one more equality. Proving that XY plus YZ equals AW plus WX will do the trick. Let's construct the point H as being the midpoint of the side AD. And we will draw the line BH. Now, in the drawing, we see that BH is collinear with BX. But that is not something we can assume. We know that BX is perpendicular to AE, but we do not know what the status of BH versus AE is. For all we know, it could well be that BH is not perpendicular on AE. In that case, BH and BX would not be collinear. Let's for the moment assume BH is perpendicular on AE. Later on we will come back and prove that is actually the case. In that case, we will consider the triangle ADZ. HX is a mid-parallel of that triangle because, first of all, H is midpoint of AD, and secondly, HX is parallel to the triangle side DZ. Ergo, X divides the triangle side AZ in two equal parts, and that's what we needed because those parts are XZ and AX. And that proves the last equality that we needed to conclude that AW equals WX equals XY equals YZ equals ZE. But we still have to prove that BH is perpendicular to AE. We only assumed it, because that's what's needed for HX to be the mid-parallel of ADZ. To do that, let's look at the quadrilateral BCEX. We need to prove that the angle in X is a right angle. As the angle in C is a right angle because it's a square, having X a right angle means that the sum of the angles in B and E must be equal to two right angles, because the sum of all angles in a quadrilateral is 4 right angles, or 360 degrees. To prove this, we will consider the two right triangles ABH and ADE. These two triangles are congruent because they have two equal sides and same included angle. Clearly, one of the sides is equal because it's the side of the square, and the other is equal because it's half of the side of the square in both cases. And the included angle is the right angle. So that means that the angle in A of the triangle ADE is equal to the angle in B of the triangle ABH. The outside corner angle in E of the triangle ADE is thus equal to a right angle plus the angle A. On the other hand, the angle formed by XBC is equal to a right angle minus the angle A. Thus, the sum of the angles AEC and XBC is equal to a right angle plus a right angle minus A. So A cancels out, and we finally can conclude that AEC plus XBC is equal to 2 right angles, which proves that the angle in X of the quadrilateral BCEX is a right angle, and so BH is perpendicular to AE. And with that, we have finally proven that the equality of the 5 segments is a given. As a bonus, there's still some nice stuff to be said of this construction. First of all, because the opposing angles in the quadrilateral are supplementary, which means the sum is 180 degrees, we know that the quadrilateral is inscribed in a circle. Secondly, analogous to the proof that BH is perpendicular to AE, we can do the same for the segment DI, constructed by connecting the point D with the midpoint of the side BC. DI is in a similar way perpendicular to AE, and we can prove this by looking at the quadrilateral ABIZ. And likewise, this quadrilateral is also inscribed in a circle. Well, that's it for this time. Thanks for watching. I hope you found this video enjoyable, and while I cannot promise a regular release schedule at all, it would be wonderful if you could subscribe and share.